Today's video is about RC servos. So in our prototype test bed, we need some instrumentation, something to measure and display what the servos are doing, so we can learn about the servos, do something to apply to the servos, manipulate the servos. And it's something we need in the test bed. That's why we built the prototype test bed in the first place. Is it's an easy way to measure things, put electronic pins into it without building something specifically on a car, right? So we can prototype it, develop it in a test bed. It's much quicker and much easier to do. So I need to do something with the servos, because that's going to be an important part of what we're going to do in the future. So electronically, what does the servo look like? So in an RC car, RC anything, typically you have a receiver. That receiver provides a bunch of connections. Let's blow this up. This is a typical 3-pin servo, a signal, +6, and ground. Okay, and that feeds into something you're going to control. This could be, let's see, throttle. This could be steering. And this could be anything else. There's a bunch of them. You have multiple channels. They call them channels. Let's call this aux, because that's kind of what we have set up on our prototype board. This is typically where the battery comes in. Feeds voltage into the throttle because it's got to drive a motor, right? Well, this also tends to provide the 6 volts to feed everything else. So there's a connector for each one of these aux connectors. So the 6 volts tends to be distributed from the battery through the motor controller into this receiver that distributes it to these servos. So then these signals go into the steering, aux, and throttle. So throttle, of course, the signal controls the motor speed and direction, or braking. Steering is left and right, and auxiliaries on or off, or some variable that can be used to do anything else other than throttle steering, some other auxiliary function. And there can be multiples. It could be 6 or 7 or 8, or who knows. In our test bed downstairs, we have we have a throttle, which is the motor, the steering, and an aux. And we'll need an in and an out eventually. So physically, that's what it's going to look like. Electrically, the servo, if you go on an oscilloscope, where you have time and voltage, right? The oscilloscope shows, sine wave, which is like AC current, or audio, like music. In this case, it's the servo signal is a pulse signal in it. So it's a digital pulse, right? And it's repetitive for redundancy and to reflect changes quickly. Okay, so these electronic waveforms, these pulses, to measure it in software, we need to measure this time frame. So in ESP32 processors, you can assign a pin and interrupt and service it with a routine. So we can also say on rising edge interrupt, on dropping edge interrupt, or any transition interrupt. So in this case, we'll define the pin. This is pin 1. Say pin 1 is an input, and it's got a pull up on it, and it's going to interrupt. And it's going to go to read servo 1. So down here you'd have a read servo 1 routine, and in there you'd say, you're in this routine because an interrupt happened, either rising or falling edge. So the first thing I do is probably say, is pin 1 high? True. If it is, I just started the clock. So I'm going to say, read the microsecond clock. it started to rain. And put it in a register. And else subtract current timestamp, the current time here, from the initial read. That'll give me a microsecond value of that right there. So how many microseconds? And then I'll put that in pin 1 read, whatever. And that'll be a variable that we'll use later to display it. And the same thing we do for Servo 2, Servo 3, Servo 4. So when the rising edge occurs, take a snapshot of the microsecond clock. When it goes low, which is the else statement, goes low, okay, take a snapshot there, subtract the 2, put that in pin 1 read value. So that's how we'd read it in software, okay? Once we read that pulse in the software, and then while you're doing the interrupt routine, it puts everything else on hold. So it comes and does it, read, puts it on hold. On a Servo 2, it puts it on hold. So then you have another servo being read, or a third one, right? And the way these work, they basically don't put them at the same time. They're on the same signal. So that'd be pin 1, pin 2, pin 3. It could be any pin number. This would be like steering, throttle, auxiliary. So this interrupt routine would quickly exit, go capture that time. This one would do the same thing, this would do the same thing. Meanwhile, your loop program is saying, hey, in the loop, display 1, display 2, display 3. And I would probably do a bar graph because they have a really cool graphic. They draw a rectangle in the M5Stack cores. It says from here to here, draw a rectangle and make it blue, right? That'll be the value. And then from here to here, make the value brown. Now I have a bar graph, and I might as well in the background of this, put the value in here, right? In the background. So you can actually see this thing move and have multiples of them. Right? So up to 6 bars probably on the screen because I have 6 inputs, and I might want to display servos, steering, auxiliary in, and output for whatever device I'm doing under test. And then this would have a bar. As the values changed, those bars would slide and represent separately. Very simple routine. All it's going to do is just keep displaying, updating this displays in the background and the interrupts. When the interrupt comes in, measure the time of it. So we're going to do that. We're going to put that in a gray. So we're going to use an M5Stack Gray. It's got all kinds of pins I/O on it. There's 6 on here. I'm going to use 4 from this side and 2 from the top. I'm going to use pins that aren't used for anything else, like the LEDs or the SD card or anything else, so they have to be unique. And I want to be able to make them pull-ups, because if you don't have a pull-up capability, they pick up noise real easy. So I kind of narrowed myself down to about 6 pins I'm going to use. That's about all I need to display on this anyway. So let's go write the code and then take us to the prototype lab bench and show it in action, hopefully. Okay, we're back to the prototype bench. If you remember in our very first video, we built this test jig. It's kind of a standalone place where we can do some prototyping electronic stuff. We have 2 servos, 1 aux, 1 on steering. We have a motor, got a little flag on it, so you can see it spins. It's got a motor controller, it's got a receiver, breadboard, so we can break out all the servo signals and the voltages and all that stuff. We have RCA phono jacks that go off to our digital scope. We have test points, so we can plug scopes and digital voltmeters and stuff into it. We have a power distribution area for taking the battery voltage into this. And what else? This is where we would be putting our data logger for testing. But to start getting our test bed, our electronic fixture working, we're adding a servo diagnostic capability to it. So we're adding this guy. we went back, we did a whiteboard and explained what we're going to do. We got the software done. This is a software display of 6 different servo inputs. Right now we have 3 wired up. One's for steering, one's for throttle, and one's for auxiliary. And the digital numbers on the right are the digital value of the timing we're measuring between the pulses, as we showed in the whiteboard. And the scope is also showing it. It's a digital storage scope. And it also shows the actual size of those pulse widths on the screen, which is kind of handy, but you don't want to take that everywhere. I think it's huge. It's heavy. This is portable. I can take this. It's kind of a quick diagnostic tool, quick checks and balances. The neat thing is it's 6 channels, so that's only a 4-channel scope. We can actually measure 6 servos. So if we're doing something cool, like one of our what goes into doesn't come out of models, like we do traction control, where you need to control the steering based on G-forces, or you want to control throttle for traction control or something crazy, we need to have a way of displaying what comes in from the receiver and what goes out to the servos. So we got all that in one package here. So that's the overview of the test bed. We've added the servo measurement function. So let me zoom on this guy. As you can see, we have steering, and this is the radio. So if I do the steering, full clockwise, which is right-hand steering, it goes to 1,043 microseconds, or 1 millisecond basically. And over here it says 1,040. This is 1,042, 43. So I think our digital readout here is actually more accurate than the scope. But you can see if I make it clockwise, it's 1,000. Make it counterclockwise, it's 1925 on our digital scope. And on the real scope, it's 1920. So they're right in sync. So steering is now measuring properly. Throttle, let's go reverse. Throttle reverse goes to 1,100. And the green trace on the scope goes to 1,100. So it's red on the Arduino, and it's green on the scope. I could probably change those colors, I guess. The white is the steering on the scope, and it's blue on the Arduino. So you can see I'm messing with the white trace on the top. Shorter pulses, wider pulses. Throttle, same way. Reverse, shorter pulses. Throttle up, wider pulses. Pretty cool. And then if you'll see aux, if I turn aux on, it goes to 1920. And the green, yellow trace says 1922 or 1920 now on the orange yellow scope trace. So that's also the aux servo you're hearing moving around in the background. So we now can measure these guys. It works. Kind of pretty too. Awesome. So our test bed is upgraded. The next thing you'll probably see us with the test bed is with the RC logger, where we'll actually be logging these servo numbers into the logging device. Pretty cool. And that'll be next.